The next topic is basis for a topology. So let us recall that in all the examples of topological spaces that we have seen so far, for instance, finite complement topology, discrete topology, in each case we described the topology by specifying all the open sets. Usually this is too difficult to do because the spaces we will encounter, there the topologies and the open sets are really very wild and things are big. It's difficult to say what all the open sets are at once. That's why what we do instead is that we take a small collection of subsets of the set on which we want to describe a topology, and then with the help of that collection we are going to somehow generate the topology. And such a collection of subsets will be called a basis for a topology, for some topology on that set X. Just like you have bases in a vector space. Most of the time, in order to describe a vector space, you don't really specify all the vectors. Instead, you specify a basis, you say what the basis vectors are, then you know what all the vectors are. They are linear combinations of the basis vectors. So like that we are going to see basis of topological spaces. So let's start with the definition of a basis. And the definition is this. So let's see carefully what the definition says. Let X be a set. So obviously we have to start with a set X on which we want a topology. A collection B of subsets of X is called a basis for a topology on X if the following conditions hold. But let us stop here itself and try to understand this part. What is B? B is a collection of subsets of X. That means the elements in B are subsets of X. Just like the elements in a topology are subsets of X, like that. And it will be called a basis for a topology, a basis for some topology which still we don't really know how this basis is going to give us a topology, that will come afterwards. On X, if something happens, but let us also concentrate on this indefinite article A basis. So whatever topology this B ultimately will give us, for that topology, this is not going to be the only basis. There may be others. That's why A basis. And it matches with what we have in linear algebra, for example, where you consider a vector space. Vector spaces have bases, and a vector space usually has more than one basis. So the situation is the same here also. But such a B will be called a basis for some topology on X if these things happen. Now let us see what these conditions are. The first condition is this: for each point X in the original set, there exists a set N in B. Recall that the elements in B are themselves sets. These are some subsets of X. So for each such X in X, there exists an N in B such that X belongs to N. What does it mean? I mean, of course, we have seen just now what it means, but actually, how can you think of it? It can be phrased slightly differently. If we call the elements of B basis elements, that is, if we call these N's basis elements, then this condition tells us that every point of X is contained in some basis element. Or in other words, that if you collect all these basis elements, all these N's, they are subsets of X, together they cover X. That anything that we have in X is inside at least one N. So together they are covering the entire set X. Or to be more precise, if you take the union of all these n's in B, then that is equal to x. How? Well, obviously each n is a subset of x, so their union, if you take, that will also automatically be a subset of x. But at the same time, this condition ensures that the reverse inclusion is also true. You take any element x in x, it is in some n. So obviously it will be in the union of the n's. So you get this fact that, in fact, this is what you should remember, that the n's are sufficient in number, and in the sense that if you take the collection of all n's, then they entirely cover x. So that is condition 1. And then what about condition 2? If x is in x and you encounter two basis elements, n1 and n2, that means they are elements in B, such that x is contained in their intersection, that is x belongs to both of them, then there exists another basis element n3 which contains x and which is itself contained in n1 intersection n2. So this second condition means that, say you have two basis elements n1 and n2 and both of them contain some point x of x. Then there is a third basis element which will contain that point and will itself be contained in the intersection of these two basis elements. If these two conditions are true, then such a collection of subsets B will be called a basis for some topology on X. But what is that topology? That comes next. Okay, so next comes the topology generated by this basis B. If B satisfies the above two conditions, those two conditions in the definition of a basis, then we define the topology tau generated by B as follows. Okay, so the topology that this basis B will generate, we are calling it tau. And what will be the elements in tau? A subset U of X is said to be open in X. In this topology, that means U is an element in tau if this condition is true. For each X in U, for each point X in U, there exists a basis element N such that X is in N and N is itself a subset of U. You can understand that more clearly with the help of this Venn diagram. So this rectangular region represents your set X, in which you have this subset U given by this irregular region. The condition is that no matter what point X of U you choose, there should be a basis element, some basis element in your basis which contains that element X inside of it as an element and should itself be entirely contained within U. If even one X in U fails to satisfy this condition or causes problem, then U will not be open. Say you encounter some X somewhere which is not contained in any N. Well, condition 1 ensures that that X, after all being an element of X, will belong to some N. But that's not the only thing that you should have here. That N itself should be entirely contained in U. Maybe the N that this X belongs to, that is not a subset of U. You may get some N's which contain that X as an element in it, as an element in them, but none of them is a subset of U. If you encounter at least one such point in U, then by this condition U will not be open. Okay, so it will not be an element in the topology. So that's how we define the topology, and that is we are saying that it is being generated by that basis element B. And you can observe one more thing, that B itself is a subset of that topology. In other words, every basis element itself is open. How? Well, let me modify this diagram. Say in place of u, now I have an element n of B itself. Will this satisfy this condition? Will this n satisfy this condition? You take any element x in n. Okay. What do we then need? We need a basis element that will contain that x and will be itself a subset of n. But one such obvious element is n itself, because n already itself is inside the basis and obviously it contains x and it is a subset of itself. So that way any element n in B is also open, automatically open by this condition, and so it will belong to tau, and that way the basis itself becomes a part of tau, which is what we want. We want the basis to somehow be only a small part of the entire topology, and it should somehow be able to give us all the open sets, in spite of itself not likely having all the open sets, but its elements are also open sets. We still have to prove that the way we have defined this tau, that it really is a topology. That means we have to verify all those three conditions in the definition of a topology. That we won't do today. Okay. Instead, let us see some examples of bases. So let us next see this example 1. The set X in this case is the two-dimensional plane. That means the set of all points in the two-dimensional plane. And on this plane, let B be the collection of all circular regions. That means interiors of circles. Then B is the basis for some topology on the plane. How does B satisfy those two conditions in the definition of a basis? The first condition requires that any point in the plane has to be inside one basis element. That means has to be inside the interior of some circle, which is obviously true because you take any point in the plane. Let me actually draw a diagram here. So this is any point in the plane. Then obviously you can draw a circle which has that point in its interior. The drawing is not good, but you get the point. Okay, this is the circle. So you can draw a circle sufficiently large and in a convenient manner so that the point lies in the interior of the circle. To be somewhat more aesthetically pleasing, you can choose a circle which has that point as its center. That also you can do. So that means the condition 1 in the definition of a basis for this collection is obviously true. Next we come to the second condition, and for the second condition let me draw a diagram. So the second condition is that if you take two basis elements, which in our case now are interiors of circles, say this N1 and N2. N1 here looks like an ellipse, but it says circle. Okay, assume that it says circle, and a point in the plane which belongs to both of them. Say that point is this X. Then you should also be able to have another basis element N3 which contains that point and is itself contained in the intersection as a subset. Obviously, no matter how small this intersection of the two circles is, and no matter where this point X lies in that intersection, you will be able to find a circle small enough, and for the sake of specificity and simplicity, let us take that circle as having that point as the center. You can choose the radius so small that the resulting circle will be entirely contained within this intersection. If you really want to rigorously prove it using the axioms of geometry, it will take a long time, but that's not the point here. The point here is that we know that it will happen. Okay, so that is why condition 2 is also true in this case, and this is a legitimate basis for some topology on the plane. And in that topology, a subset U of the plane will be open if every x in U lies in some circular region contained in U. And note one more thing, that these open sets themselves need not be circular region, although the circular regions also are open sets in this topology that we saw previously itself, that B itself is contained in tau. But there may be other open sets of pretty irregular shapes. For example, let me draw another diagram. So this exact region, the region enclosed within this simple closed curve, that is really an open set in this topology. The boundary is not there in this set, so without the boundary. And why is that so? If you choose any point anywhere inside this region, you can obviously draw a circle containing that point and which is entirely contained in this subset. You may think that if you choose your point very close to the boundary, you will have some kind of difficulty. Well, you have to be careful. The circle that you will draw, which will have that point inside of it and which should entirely be contained in this region, it should have sufficiently small radius, but you get the point. I mean, because the boundary itself is not a part of this set, so you cannot choose a point to lie exactly on the boundary, so there will be some gap, and that gap can be used to draw a circle which will contain this point and will itself be entirely contained in this U. And that's why such ugly looking amoeba type of shapes also will be open in this topology. And there is a variant of this in the next example. In example 2, we again have the set of all points in the plane, that is our set, but this time we are considering the collection B prime, and this time it's the collection of all rectangular regions in the plane, interiors of rectangles. In the previous one, the regions were circular regions, now rectangular regions, and where the rectangles have sides parallel to the coordinate axis. So that means they are like this. Okay, not oblique like this, but like this. And this B prime turns out to be a basis for some topology on the plane. So let us verify that, just like the previous example. The first condition is that each point in the plane must be inside some rectangular region, which obviously is true. From simple geometry, we know the fact. So you take any point on the plane, so there is such a, in fact there are infinitely many rectangles that will have that point in their interiors. So condition 1 is true for this collection B prime. For condition 2, you take two such rectangles and so that they are intersecting. They are, you see, intersecting means what? Do not forget that we are not considering the actual rectangles, but rather the interior regions of the rectangles. So if two such interior regions intersect, they cannot just simply touch each other like this. They have to intersect like this. The regions have to intersect. And say there is a point X within that region. In this case, the second condition is easier than the previous example, because the intersection itself is another such rectangle. So in this case, you can choose this intersection itself to be N3. So obviously that contains X, and N3 is contained in N1 intersection N2 because it is equal to N1 intersection N2. So yes, this also is a legitimate basis for some topology on the plane, and we will see later that this topology and the previous topology are actually the same. So here itself you have an example of a topology which has two different bases, one consisting of circular regions, the other one consisting of rectangular regions. And let us see one more example. In this third example, it's a little different. Here X is any set and we are considering the collection of all one-point subsets of X, which also are known as singleton subsets. That is the basis for some topology, and you know that topology, the discrete topology on X. Let us see how. So we have the set X here and we are calling this collection B, the collection of all singleton subsets of X. Let's verify the first condition for a basis. For every X belonging to X, the singleton set consisting of that element X obviously is in B, because B is the collection of such sets, such that X belongs to this. So every point of X is contained inside some basis element. Although actually at this stage, before proving that it's the basis, we should not perhaps say basis element. Every point is contained in some element in B. Now we go for the second condition. So for the second condition, we take any element X in X and say we have two basis elements N1 and N2. So by definition, each one of them has to be a singleton set. So this one is the set A and this one consists of B. In B, such that X belongs to their intersection. Now X belongs to the intersection of these two singleton sets means what? That they really intersect, that they are not disjoint. However, that immediately implies that X must be equal to A and A must be equal to B. But then we have this other basis element N3 consisting of that only element X in B, such that, again I said basis element, an element in B such that X belongs to N3, of course, and N3 is not just contained in this intersection, but it's actually equal to this intersection, because in this case N3, N1 and N2 are same. So yes, this really is a legitimate basis for some topology on X. But why is that topology the discrete topology? Recall the definition of discrete topology. The discrete topology is the collection of all subsets of X. So that means that this will generate that topology. So under that topology, every subset should be open. Is that true? Let's see. So let us take any subset U of X. Let us first handle the case where U is the empty set. In this case, the condition for openness is vacuously true. How? Well, what is the condition for openness? That for any X in U, there should exist a basis element. Now we can call it basis element, okay, these things, because we have already shown that they form a basis, such that X is contained in that N, and I mean as an element, and N itself is contained as a subset in U. What is the structure of this sentence? It's an implication, it's an if-then statement. And the hypothesis of this implication is this statement: if X belongs to the empty set, which is false, and that is why the implication is vacuously true, but true nonetheless, and that is why the empty set is open. Now next let us see the case where U is non-empty. Next let U be non-empty, and let us take any element X in U. Then we have this basis element, this singleton set consisting of X, such that X is contained in that set as an element and is itself contained in U as a subset. Why is this containment true? Because X is an element of U after all. So that way, in this case also U is open. So we see that just about any subset U of X is open. So every subset is open, that means the topology is the discrete topology. And let me just end the video here itself. Next week on topology, we are going to first of all prove that the way we have defined the topology generated by the basis B, that really is indeed a topology. And then we are going to formulate a way of expressing general open sets in that topology in terms of basis elements, which will not exactly be the definition itself. Actually, let me tell you how the open sets can be understood in terms of the basis elements in a different way than the definition. Any open set will be a union of some basis elements. That's what it is. Just like any vector in a vector space is a linear combination of basis vectors, in this case any open set in a topological space is going to be a union of basis elements. Not necessarily finite union, but a union of basis elements. And then there are other things also. We will see how we can decide only from bases. Say two topologies are given, but we don't really know them fully, but instead their bases are given. How we can decide only from looking at the bases which one is finer, which one is coarser. So these things are also there. And of course then the journey is very long. So see you next week with these things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.